All right, today we're tackling a big one, organic chemistry. Now I know, that sounds kind of complex, maybe even a little scary, right? But stick with me, because it's literally the secret code behind, well, you, me, and pretty much everything you can touch. So let's jump right in. And that is no exaggeration, folks. This quote, it gets right to the heart of it. We're talking about the essential molecules that, build and power all living things. Without them, life as we know it, it just wouldn't exist. Simple as that.
So what does that actually mean in your day-to-day life? Well, think about this. We're talking about your DNA, the very blueprint that makes you, you. We're talking about the fuel that gets you from A to B in your car, the medicines in your cabinet, and yep, even the clothes you're wearing right now. All of it, it's all organic chemistry in action.
But here's the crazy part. We didn't always see it like this. For a long, long time, scientists actually believed that organic compounds could only be made by living things. They thought there was some kind of mysterious vital force at play, almost like there was something magical about the chemistry of life that we couldn't replicate.
And then 1828 happened. Everything changed. A chemist, Friedrich Wöhler, was in his lab and he accidentally created urea, a key organic compound from something totally inorganic. Boom! Just like that, this one experiment completely shattered the whole vital force idea. It proved that the chemistry of life and the chemistry in the lab were governed by the same rules. And that right there opened the floodgates for the modern science we have today. Okay, so what's the secret? What makes all of this incredible diversity possible? The answer comes down to one single element, the absolute, undisputed star of the show: carbon. You can think of it as the ultimate Lego block for building the entire molecular world. Now, carbon has a couple of superpowers that make it just perfect for this job. And it all starts with its first one, this incredible ability to link up with itself over and over and over again. This superpower has a fancy name. It's called catenation. And it's what allows carbon to form these super strong, stable bonds with other carbon atoms, creating those massive chains and complex rings that are the backbone of, well, everything. From simple plastics to the unbelievably intricate double helix of your DNA, no other element can do it this well. Not even close. And for its second superpower, it almost always forms four bonds. See, it's not just that it forms bonds, it's how it does it. Carbon is just incredibly consistent. It's programmed to form exactly four stable bonds. And this simple rule is the key to building all those complex three-dimensional structures. 4. That's it. That's the magic number. It might sound simple, but this one rule, carbon always makes four bonds, is what gives it the power to build the vast and intricate 3D architecture of life itself. So, with literally millions of these compounds out there, can you imagine trying to draw every single atom and bond? It would be a total nightmare. So chemists about smart. They came up with a really clever shorthand, an elegant visual language to draw these incredibly complex molecules. Okay, so on the left, you've got the complete formula. It shows every single atom. And yeah, it's technically correct, but man, it gets cluttered fast. But now look at the right. That's the bond line formula. It's this clean, zigzag line where every corner and every endpoint is just assumed to be a carbon atom. It's clean, it's simple, and it lets you focus on the carbon skeleton, which is really the heart of the molecule. And what's amazing is that these bonds create just three basic shapes. If you have four single bonds, you get a 3D pyramid shape. If there's a double bond in there, the structure flattens out like a triangle. And if you have a triple bond, it snaps everything into a perfectly straight line. So here's the key takeaway. Every single organic molecule, no matter how ridiculously complex it looks, is really just a combination of these three simple shapes.
All right, so if the carbon skeleton is the basic structure, what gives a molecule its unique personality? That's where functional groups come in. The best way to think about them is like accessories. They're these little attachments you can add to the carbon backbone that completely change how a molecule acts and what it does.
So a functional group is basically the active site of a molecule. It's the part that actually gets involved in chemical reactions. It's what determines if a molecule is going to be an acid or an alcohol or something else entirely. This is where all the action happens. And this is how we connect that abstract chemistry to stuff we all know. You see an OH group? That makes it an alcohol. Yep, the kick in wine and beer. That COOH group, that's a carboxylic acid. It's what gives vinegar that sour taste. And an NH2 group makes an amine, which is a key part of proteins. See, it's these different groups that give each molecule its own distinct character.
Okay, so we know how these molecules are built, and we know how they get their unique personalities. But how do scientists actually read the chemical blueprint? How do they figure out what a substance is when they find it or create it in the lab?
I mean, that really is the big question, right? If there are millions of these molecules floating around, how on earth do scientists tell them apart? If you have a vial of some mystery gunk, how do you figure out exactly what's inside on a molecular level?
Well, chemists have a pretty slick and systematic toolkit for this. First, they have to purify the sample, often using a cool technique called chromatography to isolate just one type of molecule from the messy mixture. Then, they do what's called qualitative analysis to figure out which elements are in there. And finally, quantitative analysis tells them how much of each of those elements is present. The bottom line here is that this is not guesswork at all. It's a science built on incredibly precise measurement. By comparing a sample against a known standard, by running it through advanced machines, chemists can figure out its exact identity and structure. It's all about nailing down those numbers.
And that brings us to a final, really powerful thought. Organic chemistry has given us the ability not just to read the language of life, but to write it too. We can analyze the molecules that exist, and we can design completely new ones from scratch. So the real question isn't just what molecules are out there, it's what can we imagine? What's the next chapter that we ourselves are going to create?